The universe is alive, conscious, a vast, infinite mind where stars are its thoughts, galaxies, its dreams, and every particle hums with awareness. Your consciousness isn't separate from this cosmic mind. It's a thread in the grand tapestry, a spark of the universal flame. Think about it. Your thoughts, your very awareness, are echoes of the universe's own intelligence. The quantum law of being binds us to it. Every intention, every fleeting desire doesn't just stay within you. It flows outward, merging with the great sea of existence. When your mind aligns with the universe's mind, reality bends. You don't observe the universe. You participate in its creation. You are not a mere being within the cosmos. You are the cosmos, aware of itself. In the 1950s, Dr. Henry Beecher, an anesthesiologist on the front lines of World War II, faced a harrowing challenge. Supplies of morphine had run out, yet wounded soldiers lay before him in agony. Desperate, he administered saline injections, telling the soldiers it was a powerful painkiller. To his astonishment, many reported significant relief, their pain seemingly vanishing. What had changed? Not the injection, it was inert, but the soldier's belief in its power. This phenomenon would later be called the placebo effect, a stunning demonstration of the mind's ability to alter the body's chemistry, releasing endorphins and modulating neural pathways as though real medicine had been given. Decades of research have confirmed the placebo effect's reach. Patients given sugar pills for pain, anxiety, or even Parkinson's disease show measurable improvements, all because they believe in their treatment. It's as though belief itself taps into an unseen reservoir of potential, rewriting the body's programming in real time. The mind, it seems, doesn't just perceive reality, it helps create it. But what if this power extends beyond the body? Consciousness, in its essence, isn't confined to the brain. Studies like the Global Consciousness Project reveal intriguing hints that our thoughts, intentions, and emotions may influence the world around us. Consciousness behaves like a vast, interconnected network, with each individual mind acting as a node, sending and receiving subtle ripples. Just as a belief in a pill rewires the body's response, focused awareness might shape the environment and even the probabilities within the quantum field. The observer effect, a cornerstone of quantum mechanics, tells us that the mere act of observing a particle changes its state, collapsing infinite possibilities into a single reality. What if this isn't just an anomaly of physics, but a clue to something far more profound? A hidden dialogue between consciousness and the universe itself. And if so, how far does this connection reach? Could we, with the power of intention alone, subtly rewrite the fabric of existence? Imagine placing a cat inside a sealed box with a radioactive atom, a Geiger counter, a vial of poison, and a hammer. The system is designed so that if the Geiger counter detects radiation, due to the decay of the radioactive atom, the hammer releases, shattering the vial of poison and killing the cat. If it does not detect radiation, the cat remains alive. But here's the thing. Since the box is locked, and we on the outside don't know whether or not the radioactive substance has decayed and released the poison, we can't tell if the cat is dead or alive. So, until we open the box to know for sure, the cat is both dead and alive. Mathematically speaking, there's a 50% chance the cat is dead and a 50% chance the cat is alive. It exists as a swirling cloud of potential outcomes, each equally real and unreal. There is no finality until an observer intervenes. This is a thought experiment known as Schrödinger's cat. The experiment was meant to illustrate the paradoxes and challenges of interpreting quantum mechanics when scaling down the behavior of subatomic particles to macroscopic objects like a cat. According to quantum theory, a particle exists simultaneously in every possible state until it is measured and observed. Therefore, the particle will actually exist in all of those states at once if there is a statistical chance that it may be located here in one state, here in another state, and here in another state. The particle is said to be in a superposition in this situation. The superposition breaks down when the particle is detected, and it selects one state over all others, which is the one that our measuring device will detect. The implications of this are mind-boggling. Schrödinger's cat, as this thought experiment widely known, never means to describe reality. Instead, Erwin Schrödinger, the mind behind this idea, wants to highlight its absurdity. It was his challenge to the emerging field of quantum theory. Schrödinger's thought experiment is just one of the many attempts to understand the strangeness of the emerging quantum field, the strange world that's sparked by one single experiment in the 1800s. Thomas Young was born in 1773, a child of rural England, destined to change the world's understanding of light and perception. He had an insatiable curiosity and was a polymath of rare talent. By the age of 14, he had mastered several languages, including Greek, Latin, Hebrew, and Persian, and had begun his lifelong journey of studying natural philosophy. But it was his fascination with light that would cement his place in the annals of science. In the late 18th century, the nature of light was one of the most hotly debated topics in science. Isaac Newton's particle theory of light had dominated for decades, suggesting that light was made up of tiny corpuscles. However, there was a growing suspicion among certain circles that light might behave more like a wave, an idea first proposed by Christian Huygens. Young, a physician by training but a physicist by passion, was not one to shy away from challenging conventional wisdom. Young's early research included detailed studies of the human eye and how it perceives color, which led him to suspect that the behavior of light might be more complex than Newton's theories allowed. He was particularly intrigued by the phenomenon of diffraction, the bending of light waves around obstacles, which seemed inexplicable if light were merely a stream of particles. In 1801, Young conducted the experiment that would forever change our understanding of light. He designed a deceptively simple setup: a light source, a barrier with two closely spaced slits, and a screen to capture the resulting pattern. It was, at its heart, an elegant test of whether light behaved like particles or waves. If light were made of particles, one would expect two bright spots on the screen where the light particles passed through the slits. But if light behaved like a wave, Young predicted something more intricate, a pattern of alternating bright and dark bands, the result of interference between overlapping light waves. Young's experiment was meticulous and deliberate. He knew that waves, like ripples on the surface of a pond, could interfere with one another, either amplifying or cancelling out, depending on how their crests and troughs aligned. If light were indeed a wave, then the waves emerging from the two slits would interact, creating regions of constructive interference, bright bands where the waves reinforced each other, and regions of destructive interference, dark bands where they cancelled each other out. The experiment was a triumph. When Young shone light through the two slits, the screen displayed a series of bright and dark fringes, unmistakable evidence of wave interference. It was a breathtaking discovery. Light, it seemed, was not merely a particle, but also a wave. A revelation that defied the simplicity of Newtonian physics. The double-slit experiment became a cornerstone of wave theory, a beautifully simple demonstration of light's dual nature. For decades, Young's findings stood as a testament to the wave nature of light. But his experiment wasn't just a triumph of optics, it was the beginning of a much stranger story. By the early 20th century, quantum mechanics began unraveling the secrets of the universe at its smallest scales. It was 1927 when Clinton Davison and Lester Germer, two US physicists, decided to test Young's experiment with electrons instead of light. Their goal was to determine whether matter, tiny, seemingly solid particles like electrons, could also behave like waves. They fired a beam of electrons at a barrier with two slits, just as Young had done with light. On the screen behind the slits, they expected to see two bright spots where the electrons passed through. After all, electrons were particles, right? But when they looked at the screen, they were astonished. Instead of two distinct clusters, the electrons formed an interference pattern, a series of alternating bright and dark bands, just like light waves. Somehow, each electron seemed to pass through both slits simultaneously and interfere with itself as though it were a wave rather than a particle. It was an incredible revelation. Matter, it seemed, was not what it appeared to be. The experiment was repeated, refined, and scrutinized, but the results were consistent. Electrons, and later even larger particles like atoms, behaved as waves when they passed through the slits. The implications were staggering. If matter could act like a wave, then particles were not tiny, solid points, as classical physics suggested. But the real mystery emerged when the two decided to observe the electrons directly. To solve the enigma of how a single electron could pass through two slits at once, they placed detectors at the slits to determine which slit each electron passed through. The results were shocking. The interference pattern vanished. Instead of behaving like waves, the electrons began acting like particles again, forming two distinct clusters on the screen. At first, they thought they had faulty equipment, and then repeated the experiment again. The results turned out to be the same. It was a repeatable and predictable process. The very act of observing the electrons changed their behavior. When unobserved, the electrons existed as waves of possibility, simultaneously exploring every possible path. But the moment a measurement was made, when the electrons were observed, they collapsed into one definitive state, behaving like classical particles. This phenomenon challenged everything physicists thought they knew about reality. How could simply looking at something alter its fundamental nature? What was it about the act of observation that caused the wave of possibilities to collapse into a single outcome? To make sense of Davison and Germer experiment, Niels Bohr another pioneers of quantum mechanics, proposed an interpretation. According to Bohr, particles exist in a state of superposition, a blend of all possible states, until they are observed. Observation forces the particle to choose, collapsing the superposition into a single reality. Imagine you're standing in a vast, dark space, watching a swirling mist of glowing particles. It's not just any mist, though. This one is alive with possibility, shifting and flickering as if it's undecided about what it wants to be. Some particles are here, others are there, speeding and changing direction in every possible way. This is the quantum world, where everything exists in a state of superposition, many possibilities happening all at once. Then, imagine someone walking into this scene, a figure holding a powerful light. As they step closer, the particles seem to notice. There's a sudden shift, like the air itself gets still. The moment the beam touches the particles, everything stops. The once chaotic mist solidifies into something clear and defined. A single particle, frozen in place. The possibilities are gone, and only one reality remains. This moment of change is what Niels Bohr called the observer effect. Before the observer arrived, the particles were free to be anything, uncertain and undefined. But the instant the observer looked, the particles were forced to pick a state. But what counts as observation? Is it the presence of a measuring device, the interaction with other particles, or is it something more profound, tied to the presence of a conscious observer? Werner Heisenberg adds another layer to this mystery. He proposed something even more unsettling. What if the act of observing doesn't just collapse the wave of possibilities, but also changes the very nature of what you're trying to observe? Imagine you're holding a tiny ball, so small that you can't quite see it directly. Instead, you use a flashlight to shine a beam of light and catch a glimpse. But here's the catch. The moment the light hits the ball, it changes its position. You can't know exactly where the ball is without disturbing it. And the more precisely you try to measure one thing, like its position, the less you can know about something else, like its speed. This is Heisenberg's uncertainty principle. Because the act of measurement involves interacting with the system, you can't pin down both the location and momentum of a particle at the same time. It's like you're trying to track the motion of a dancing firefly in the dark. Each time you shine a light to get a closer look, the firefly darts in another direction, making it impossible to know exactly where it is and where it's headed. The more you shine the light, the more you disturb its dance. It's as though the very act of trying to measure it forces the firefly to change course, revealing only part of the story, never the whole picture. In Heisenberg's uncertainty principle, observation is not just about looking or measuring. It's about the unavoidable interaction between the observer and the system. The observer becomes part of the reality they are trying to observe. This means that the very nature of what you're measuring is forever entangled with the way you measure it, and the more precise your observation, the more you interfere with the system itself. But why this happens? Could it be that consciousness itself plays a role in the way the quantum world behaves? Can the act of knowing something be so powerful that it creates reality from the unseen? Roger Penrose didn't begin his career searching for the mysteries of consciousness. His world was one of mathematics, of geometry and abstract patterns. Yet somewhere along the winding road of his intellect, he stumbled upon a question so profound it demanded his full attention. What makes the mind different from a machine? For decades, scientists had assumed the brain was simply a biological computer, neurons firing like circuits to create thoughts, emotions, and awareness. But Penrose wasn't convinced. Something about this explanation felt incomplete, almost mechanical. He began to wonder if consciousness, that elusive spark of self-awareness, might arise from something deeper, something rooted in the fabric of reality itself. His intellectual curiosity led him to collaborate with Stuart Hameroff, an anesthesiologist fascinated by the brain's mysteries. Hameroff had spent years studying microtubules, tiny structures within neurons that seem to play a critical role in how the brain processes information. Together, Penrose and Hameroff proposed a radical theory. Consciousness wasn't just the result of chemical reactions and electrical signals. It emerged from quantum processes happening within these microtubules. They called their theory OR, short for Orchestrated Objective Reduction, and it was as bold as it was controversial. To understand OR, you have to think about the brain not as a computer, but as a quantum orchestra. Each microtubule acts like a musician, vibrating with quantum states that are both here and there, both now and then. These quantum states interact, forming patterns of superposition that hold immense amounts of information. But there is a catch. These patterns don't remain in superposition forever. At a certain threshold, they collapse into a single state, much like the wave function of a particle in the quantum world. This collapse, Penrose and Hameroff argued, is what creates a moment of conscious awareness. It's the transition from possibility to reality, from potential to perception. Imagine this: the brain as a vast, shimmering network of quantum possibilities. Each microtubule hums with the potential for countless thoughts, ideas, and sensations. But it's not until these possibilities collapse into coherence that they become something tangible, something you can think or feel. It's as if consciousness itself is the act of the universe making up its mind, one quantum decision at a time. The idea was revolutionary, but it wasn't without its critics. Many neuroscientists dismissed it outright, arguing that the brain was too warm, too noisy for quantum effects to play any meaningful role. Quantum mechanics, they claimed, belonged to the cold, isolated world of particles, not the messy, chaotic realm of biology. But Penrose and Hameroff pressed on, pointing to experiments that hinted at quantum coherence in biological systems. They believed the brain's microtubules might be uniquely suited to harness quantum processes, acting as a bridge between the physical and the mental. Think of a drop of water trembling on the edge of a leaf. It holds a perfect curve, suspended between the forces of gravity and surface tension. For a moment, it exists in a delicate balance, a state of potential. Then, with a single nudge, it falls, its path shaped by the unseen laws of physics. This is how Penrose and Hameroff imagined the collapse of quantum states in the brain. Each collapse is a drop falling into the stream of consciousness, shaping the flow of thought and awareness. The implications of OR are staggering. If consciousness arises from quantum processes, then it's not just a product of the brain. It's connected to the quantum fabric of the universe itself. This means that your thoughts, your awareness, might be rooted in the same fundamental laws that govern particles and waves, stars, and galaxies. But how do we test such a theory? Penrose and Hameroff suggested that certain phenomena, like the effects of anesthesia, might hold clues. Anesthesia works by disrupting consciousness, yet the exact mechanisms remain poorly understood. Could it be that anesthesia interferes with the quantum processes in microtubules, temporarily silencing the orchestra of the mind? It's a question that remains unanswered, but it points to the tantalizing possibility that the secrets of consciousness might one day be unlocked. As we delve deeper into the quantum world, we begin to see connections between the mind and the physical world that were once unimaginable. OR begins with the quantum dance inside the brain, a symphony of collapsing possibilities within microtubules, birthing moments of conscious awareness. But what if this process isn't confined to our minds? What if the universe itself operates in the same way? A vast network of quantum states collapsing not randomly, but through an intrinsic consciousness. Just as the mind orchestrates quantum coherence into thoughts and perceptions, could the cosmos weave its own fabric of reality through some universal self-awareness? The same quantum principles that give rise to our thoughts might underpin the grand design of existence itself, suggesting that the universe is not a passive expanse of matter and energy, but a living, conscious entity. And if that's true, are we merely fragments of its awareness, or something far greater? A way for the universe to know itself. Stars scatter like shimmering diamonds on the black velvet of infinity. Planets, both near and far, spin silently in their cosmic ballet, adorned with rings of ice and rock or cloaked in swirling storms of gas. The tiniest moons, pocked with ancient craters, orbit with devotion, while colossal giants, painted in swirling patterns of clouds, cast shadows across their systems. The space between them is not empty, but alive with the faint whispers of cosmic radiation and the echoes of light stretching endlessly outward. Beyond the visible lies the realm of the unseen, where dark matter holds galaxies in a gentle, invisible embrace, and dark energy presses the cosmos outward, ever expanding. Every particle, every photon dances to rhythms dictated by laws etched into the very fabric of existence. The universe is vast, and it is beautiful. But to a curious mind like Gottfried Wilhelm Leibniz, it was also puzzling. He saw its endless stars, its intricate patterns, its perfect balance, and he wondered, what holds it all together? What lies beneath everything we can see, touch, and measure? For him, the answers weren't just in the heavens, but in the essence of existence itself, in the invisible building blocks of reality that he called monads. Leibniz's life was a journey of relentless curiosity. Born in 1646, in the shadow of the 30 Years' War, he lived in a Europe still wrestling with science, philosophy, and religion. He was a polymath, fluent in mathematics, law, metaphysics, and theology, always searching for unity in a fragmented world. While Newton explored gravity and Descartes dissected the mechanics of the physical world, Leibniz focused on the intangible, the why behind the what. To him, the universe wasn't just a machine, it was alive, full of purpose and meaning. And at its core, he believed, were monads, indivisible, invisible, and eternal. Leibniz envisioned the monad as the simplest unit of reality, Unlike atoms, which are physical and divisible, monads were metaphysical. They weren't made of matter, but of pure energy and essence, a tiny sparks of existence. The monad does not occupy any space. It is not material or touchable or physical. Based on this, reality is not material or physical, because Leibniz says that monads are the building blocks of reality. Each monad, he argued, was a unique, self-contained universe, reflecting the entirety of creation in its own way. Imagine a mirror that doesn't just show one image, but contains the reflections of everything that has ever been and ever will be. That was a monad. And while monads never interact directly, they are perfectly synchronized, like countless musicians playing in harmony without ever seeing each other, guided by a cosmic conductor. To him, monads explained everything: the physical world, consciousness, even the idea of God. They were the bridge between the finite and the infinite, the material and the spiritual. And their harmony, he argued, wasn't random, but preordained, a concept he called the pre-established harmony. It was as if the entire universe had been wound up like a clock at the moment of creation, each monad ticking perfectly in time forever. To explain monads to the skeptical minds of his era, Leibniz used analogies that still resonate today. Picture a kaleidoscope. As you turn it, patterns shift and change, each one unique and beautiful. Yet, beneath the chaos lies order. Mirrors and light working together in perfect coordination. Each monad, Leibniz said, is like a piece of that kaleidoscope, reflecting the whole even as it remains distinct. Or think of a beehive, where thousands of bees work independently, yet their efforts create something far greater than the sum of its parts. The hive is alive because of the bees, just as the universe is alive because of its monads. Penrose's idea of orchestrated objective reduction and Leibniz's monads, though centuries apart, share a striking resemblance. Leibniz imagined these invisible, indivisible units of reality as windows without glass, reflecting the universe in their ceaseless dance. Each monad, a microcosm, whispers a story of the infinite, hinting at an intricate order no eye can see. Or, emerging from the fertile collision of quantum mechanics and neuroscience, tells a tale where consciousness isn't just a product of the brain, but a fundamental thread in the fabric of reality. Together, these ideas form a bridge, not of wood or stone, but of thought, crossing the river of time to reach a question as old as human wonder. Could the universe itself be alive, aware, conscious? The stars, those ancient pinpricks of light, might not merely shine, but observe. Such a notion seems audacious, absurd even, but is it any more so than the idea of consciousness arising from a sea of firing neurons? Ancient thinkers whispered of a world animated by a great mind. The Greeks spoke of anima mundi, the world soul, a vital force breathing life into all things. In Greek philosophy, anima mundi was the unifying principle that linked all creation. Plato, the great philosopher, gave this idea its most enduring voice. In his dialogue, Timaeus, he describes the cosmos as a single living creature imbued with a soul and intelligence. This soul, the anima mundi, permeates every part of existence, connecting the celestial and the terrestrial, the mortal and the divine. For Plato, the universe was not only alive, but also purposeful. its every motion guided by a higher order. To imagine the world as alive is to see it with new eyes. The Greeks looked to the heavens and saw not an empty void, but a vibrant, harmonious system. The stars, moving in their celestial dance, were not random but intentional, their patterns reflecting a deeper truth. The planets, the wanderers, traced paths that resonated with the rhythms of life on Earth. This cosmic harmony was more than metaphor. It was a way of understanding the interconnectedness of all things. The same patterns that governed the heavens also shaped the human soul, binding the microcosm to the macrocosm in a grand cosmic symphony. Yet, Anima Mundi was not only about the stars, it was also about the earth. The Greeks saw the natural world as imbued with spirit. Rivers whispered, trees sang, and mountains stood as ancient witnesses to the passage of time. The earth was not inert, but alive, a sacred being deserving of reverence. This perspective shaped how they lived, fostering a deep respect for the environment and its cycles. The seasons were not mere shifts in weather, but a dance of life and death, renewal and decay, all orchestrated by the world's soul. This idea found its way into later philosophical traditions, most notably through the Stoics. For the Stoics, the cosmos was a single, rational being. The anima mundi was its governing principle, a divine reason or logos that ordered all things. Human beings, as part of the cosmos, shared in this divine reason. To live well, they believed, was to align oneself with the natural order, to harmonize one's will with the will of the universe. In this way, the concept of anima mundi offered not just a vision of the cosmos, but also a guide for living, a path to wisdom and virtue. But over time, the idea of a living universe faded in the face of mechanistic science. The rise of Newtonian physics, with its emphasis on laws and forces, stripped the cosmos of its soul. The stars became objects, the earth a resource, and the anima mundi a relic of a less enlightened age. Yet, even as science demystified the universe, the longing for connection persisted. Fast forward through the centuries, through the revolutions of Copernicus and Newton, and you find a world stripped bare of spirit. Mechanism replaced mysticism. Gears and forces pushed aside the ethereal. The universe became a clock, ticking away without thought, without purpose. It was an extraordinary shift, one that reduced existence to matter in motion, governed by laws as immutable as they were impersonal. No divine hand guided the stars, no animating soul breathed life into the cosmos. Instead, reality was a vast machine, intricate yet cold, a marvel of engineering devoid of meaning. This mechanical worldview was born from triumphs of reason and observation. Copernicus's heliocentric model dethroned Earth from its central position in the cosmos, placing the sun at the center instead. With this revelation came a profound humility and also a growing sense of disconnection. Humanity was no longer at the heart of creation, but a small, peripheral player in an indifferent universe. Kepler's laws of planetary motion and Galileo's telescopic observations further reinforced this paradigm. The heavens, once thought to be perfect and divine, were now understood as physical realms, governed by the same principles that shaped the Earth. Newton cemented this mechanical framework with his groundbreaking Principia Mathematica. Here was a universe of forces and vectors, of gravity and inertia, all described by elegant equations. His laws of motion provided a unified framework capable of predicting the movement of planets and falling apples alike. For the first time, the cosmos seemed comprehensible, its mysteries reduced to mathematical precision. Yet, in making the universe intelligible, Newton also made it lifeless. The celestial spheres no longer sang, they simply spun, driven by the blind interplay of forces. This mechanistic vision extended beyond astronomy. The Cartesian split proposed by René Descartes divided reality into two realms: the res extensa, or extended substance, encompassing all matter, and the res cogitans, or thinking substance, confined to the mind. The physical world was a realm of cause and effect, a deterministic system where every event could, in principle, be traced back to its antecedent. This dualism allowed science to flourish, free from the constraints of theological explanations, but it also severed the connection between mind and matter, reducing the natural world to a mere backdrop for human thought. Mechanism's success lay in its utility. By treating the universe as a machine, scientists unlocked unprecedented power. The Industrial Revolution, with its steam engines and spinning jennies, was a direct consequence of this worldview. Nature became something to be harnessed, manipulated, and controlled. Yet as humanity conquered the natural world, it also alienated itself from it. The Earth was no longer a mother, but a resource, its rhythms ignored in favor of productivity. Even biology succumbed to the mechanical paradigm. The body was understood as a machine, its organs analogous to pumps, levers, and pipes. Harvey's discovery of blood circulation likened the heart to a pump, a marvel of biological engineering, but devoid of purpose beyond function. The soul, once thought to animate the body, was relegated to the realm of superstition. Life itself became a puzzle of chemistry and physics, its mysteries framed in terms of molecules and reactions. Mechanism reached its zenith in the 19th century with the rise of classical physics. Laplace, a French mathematician, epitomized this deterministic view. In his vision, the universe was a vast clockwork, so predictable that if one knew the position and momentum of every particle, one could calculate the entire past and future of the cosmos. This was a world without surprises, without freedom, and ultimately, without mystery. Everything, from the orbits of planets to the thoughts in our heads, was the inevitable result of prior conditions. But cracks in this rigid framework began to appear. Thermodynamics revealed a shadow lurking in the deterministic machine: entropy. The second law of thermodynamics stated that systems tend toward disorder, that energy disperses and becomes less useful over time. The universe, it seemed, was not a perfect clock, but a system winding down, destined for heat death. This bleak vision contrasted sharply with the eternal, unchanging cosmos of Newtonian physics. Then came quantum mechanics, shattering the mechanistic worldview entirely. At the subatomic level, particles did not behave like billiard balls, but like waves, their positions and velocities governed by probabilities rather than certainties. Reality, it seemed, was not deterministic but indeterminate, a realm of possibilities rather than certainties. This interactivity opens a doorway to the scientific possibility of a living universe. It's a view that finds resonance not only in quantum mechanics, but also in the burgeoning fields of complexity science and systems theory. These disciplines reveal a cosmos brimming with self-organizing patterns, emergent phenomena, and networks of interdependence. Far from being static, the universe appears dynamic, adaptive, and profoundly interconnected. Consider the web of life on Earth. From a strictly mechanical perspective, life appears to be a curious accident, a rare anomaly in an otherwise inert cosmos. Yet upon closer examination, life exhibits qualities that seem to defy the sterile determinism of a mechanical universe. Living systems, for instance, do not merely exist, they actively maintain and even increase order within their boundaries. This stands in stark contrast to the universal tendency toward entropy, as dictated by the second law of thermodynamics, which suggests that systems naturally progress toward disorder over time. Life, it seems, has found a loophole. But how? Imagine a pristine garden surrounded by a chaotic wilderness. The garden's beauty and order do not arise spontaneously, but are the result of deliberate effort. Energy, sunlight, water, and nutrients is channeled in a highly organized manner to nurture growth. Similarly, living organisms act as gardeners of their own existence. They consume energy from their environment, whether from sunlight, chemical reactions, or organic matter, and use it to build and sustain their complex structures. This process, known as autopoiesis, is a defining characteristic of life. Autopoiesis, derived from the Greek words for self and creation, is the remarkable ability of living systems to self-generate and self-sustain. A cell, for instance, continuously rebuilds itself, synthesizing proteins, repairing damage, and maintaining its membrane. Unlike a rock, which passively exists, a living cell is in constant flux, actively participating in its own survival. It is both the weaver and the tapestry, a system that creates itself anew every moment. This self-organizing principle extends far beyond individual organisms to entire ecosystems. Picture a coral reef, a dazzling mosaic of colors, shapes, and forms. Each coral, fish, and microscopic plankton plays a role in this intricate dance. The coral provides a habitat, the fish keep populations in check, the plankton serve as a food source. Together, they form a dynamic equilibrium, a balance that sustains the whole. This interconnectedness is not incidental, but essential. Remove one piece, and the system begins to unravel, much like pulling a thread from a woven fabric. From a thermodynamic perspective, life's defiance of entropy hinges on its ability to harness energy flows. Life harnesses energy gradients, such as sunlight or chemical differences, to build and sustain order. Plants, for instance, capture photons through photosynthesis, transforming light energy into the chemical bonds of glucose. This stored energy then powers countless biological processes, from cell division to muscle contraction. But life doesn't just resist entropy, it appears to thrive on it. The energy extracted from the environment comes with a cost: waste heat and byproducts. Yet these byproducts often feed back into the system, creating new opportunities for growth. Consider a forest. Fallen leaves decay, releasing nutrients into the soil, which in turn nourish new plants. This cyclical process, where waste becomes resource, is a hallmark of living systems. It's as if life has learned to dance with entropy, turning a destructive force into a creative one. Now, let's zoom out to the planetary scale. Blue. That's how Earth first strikes you when seen from the vast emptiness of space. Not green for its sprawling forests, nor brown for its deserts, but blue for the oceans that cradle the world like a shimmering jewel. When James Lovelock, a scientist with a gift for asking unusual questions, stared at our planet in his mind's eye, he saw something that wasn't just beautiful, it was alive. This was no poetic metaphor or wistful longing. He meant it literally. Earth, he thought, behaved like a living organism. And if that was true, what did it mean for us, its passengers? It began in the 1960s when Lovelock was working with NASA on a puzzle: how to detect life on Mars. The space agency wanted clever ways to analyze the Martian surface, to scrape at its sands and look for microscopic fossils or organic molecules. But Lovelock, a man who preferred to think big, had another idea. Instead of focusing on the ground, he suggested looking at the planet as a whole. Life, he argued, isn't a quiet guest. It doesn't sit idly, unnoticed. It changes everything around it, leaving unmistakable clues in the air itself. And so he wondered, what would a dead planet look like? What would a living one? Mars and Venus, as Lovelock observed, had atmospheres in chemical equilibrium. Thick with carbon dioxide, they were stable and unchanging. Earth, though, was a rebel. Its air was a wild mixture of oxygen, nitrogen, carbon dioxide, methane, and traces of countless other gases. It was restless, dynamic, and completely out of balance. For Lovelock, this imbalance wasn't chaos. It was a sign of life. It was as if the planet were breathing, its living inhabitants keeping the atmosphere alive through their own existence. The more he thought about it, the more Earth seemed less like a lifeless rock and more like something self-sustaining, something alive. Lovelock's epiphany didn't emerge fully formed, like a lightning bolt. It was a slow dawn, brightened further by his collaboration with the brilliant microbiologist Lynn Margulis. Together, they began to wonder if life did more than simply adapt to its environment. Could it also shape it? Could living organisms work together, consciously or not, to create the very conditions they needed to survive? Lovelock named this bold idea the Gaia hypothesis, after the ancient Greek goddess of the earth. He imagined the planet not as a collection of separate parts, but as a single, interconnected system, each piece influencing the others, balancing and sustaining the whole. Consider the air we breathe. Oxygen, making up a fifth of our atmosphere, is one of the most reactive elements in the universe. It shouldn't be here, not in such abundance. Left to itself, oxygen would bond with rocks and minerals, disappearing from the atmosphere as it did on Mars and Venus. But here on Earth, it's constantly replenished by plants and photosynthetic bacteria. They exhale oxygen as they soak up sunlight, transforming the energy of a star into life. Without them, oxygen would vanish, and with it, so would we. The same is true for carbon dioxide. Too much, and the planet would scorch. Too little, and it would freeze. But plants, oceans, and countless tiny organisms act as regulators, keeping the levels just right. It's a kind of planetary thermostat, finely tuned over billions of years. But this isn't some conscious effort. Gaia, as Lovelock described it, isn't alive in the way a person or animal is. It doesn't think or plan. It's more like a symphony, where every organism, ocean current, and gust of wind plays its part without ever seeing the whole. The result is a harmony that sustains life, a self-regulating system that seems almost miraculous in its balance. But what about the bigger picture? If life shapes the environment on a small scale, could it also do so on a planetary level? Lovelock thought so. To explain, he created a simple thought experiment. Daisy World. Picture a planet covered in daisies, some black, some white. Black daisies absorb heat, warming the planet. White daisies reflect sunlight, cooling it. If the planet gets too hot, white daisies thrive, reflecting more sunlight and bringing the temperature down. If it gets too cold, black daisies take over, absorbing more heat and warming things up. Together, the daisies regulate the planet's temperature without any intention or awareness. It's a simple model, but it shows how life and environment can interact in ways that maintain balance. Earth, of course, is far more complex than Daisy World. Here, the regulation happens through countless feedback loops. Take the carbon cycle, for instance. Plants pull carbon dioxide from the air, storing it in their leaves, stems, and roots. When they die, some of this carbon is buried, eventually becoming fossil fuels like coal and oil. Over millions of years, these fuels release the carbon back into the atmosphere when burned. Rivers constantly carry salts into the sea, yet the ocean's salinity has remained stable for billions of years. How? Some scientists suggest that organisms, like certain types of algae and microbes, play a role in precipitating salts, removing them from the water. It's another quiet act of balance, unnoticed, but essential. But Gaia's most remarkable feature isn't just its ability to sustain life. It's its ability to adapt and thrive in the face of change. Life doesn't simply endure entropy, it dances with it. Consider a forest. Fallen leaves decay, their nutrients feeding the soil, which nourishes new plants. Even death becomes a resource, fueling the cycle of growth. This recycling of energy and matter is a hallmark of living systems, turning waste into opportunity, chaos into order. Critics, of course, have challenged the Gaia hypothesis. Some argue it's too teleological, implying that Earth has a purpose or goal. Others question whether the planet can truly be considered a self-regulating system, pointing to instances where life has destabilized the environment, like mass extinctions caused by volcanic eruptions or asteroid impacts. Lovelock, ever the pragmatist, acknowledged these criticisms but maintained that Gaia wasn't about intention or perfection. It was about the emergent properties of life interacting with its environment, creating stability through countless small acts of balance. Perhaps the best way to understand Gaia is through an analogy. Picture an enormous aquarium, completely sealed off from the outside world. Inside, there are fish, plants, bacteria, and water, all interacting in delicate harmony. The plants produce oxygen, which the fish breathe. The fish release carbon dioxide and nutrients, which the plants need to grow. Waste from the fish feeds bacteria, which break it down into nutrients that fertilize the plants. Even the water's temperature and clarity are maintained by this intricate web of interactions. If one part of the system falters, the entire balance can collapse. Yet, when everything works together, the aquarium becomes a thriving, self-sustaining world. Earth is like that aquarium, but on an unimaginably larger scale. Forests, oceans, and microorganisms act as its caretakers, maintaining the conditions necessary for life. Unlike the aquarium, though, there's no human hand adjusting the dials. Life itself, through countless feedback loops and interactions, keeps the system running. It's a marvel of complexity, a reminder of the interconnectedness of all things. And this is not just about Earth. Expand this idea outward, and the universe begins to resemble a living organism in its own right. For some, this notion feels like poetry, for others, like science on the frontier. Among the latter was a physicist and systems thinker named David Bohm, a man who looked at the cosmos and saw something far deeper than swirling galaxies and empty voids. Bohm believed the universe was not a collection of disconnected parts, but a seamless, dynamic whole, a vast, interconnected web of energy and information that behaves almost as if it were alive and conscious. In 1952, Bohm published a daring interpretation of quantum mechanics that suggested particles weren't independent at all. They were guided by a deeper, underlying order, a quantum potential that connected everything in the universe. To Bohm, this hidden order wasn't just a mathematical abstraction, it was real, more fundamental than space and time themselves. He called it the implicate order, a reality where everything is enfolded into everything else. The visible universe, what we see and measure, he called the explicate order, the unfolded, tangible expression of this deeper unity. Imagine an ocean, Bohm said, where waves rise and fall on the surface. The explicate order is the waves, but the implicate order is the vast, unseen ocean beneath, connecting them all. To grasp this, picture a hologram, one of those shimmering images that appears three-dimensional but is encoded on a flat surface. Break a hologram into pieces, and you might expect each fragment to show only part of the image. But that's not what happens. Each piece contains the entire image, just at a lower resolution. The whole is in the part, and the part is in the whole. Bohm believed the universe worked the same way. Every particle, every atom, every living being contained the imprint of the whole cosmos within it. This wasn't mysticism, it was physics as Bohm saw it, and it had profound implications. If the universe is a vast, interconnected system, then nothing truly exists in isolation. Every action, no matter how small, ripples outward, influencing the whole. Think of how your heartbeat depends on countless cells working in harmony, and how your body, in turn, depends on the air, water, and nutrients provided by the Earth. Now scale that up to the universe. Stars are born, live, and die, scattering elements that become the building blocks of planets and life. Galaxies collide and merge, creating new structures in an endless cosmic dance. Even black holes, those enigmatic regions of space-time, play a role, recycling matter and energy into new forms. It's a system so vast and intricate that it begins to resemble a living organism, one that evolves, adapts, and perhaps even learns. But could the universe also be conscious? That's where the work of neuroscientist Giulio Tononi and physicist Max Tegmark enters the picture. Tononi's integrated information theory, IIT, proposes that consciousness arises from the ability of a system to integrate information. In other words, The more interconnected and complex a system's network of information, the more conscious it becomes. Your brain, for instance, is a master integrator, weaving together signals from billions of neurons to create the rich tapestry of your thoughts and experiences. Tononi's IIT rests on a deceptively simple premise. Consciousness isn't just about the amount of information a system processes, but how that information is structured and interrelated. Imagine a smartphone. It can process an enormous amount of data, but the information flows in a mostly linear fashion, one app at a time, one task following another. Now compare that to your brain. Neurons don't just pass information in one direction. They form loops, networks, and layers of feedback. This creates a web of interconnectivity so dense that the whole becomes vastly greater than the sum of its parts. According to IIT, it's this integration that gives rise to the subjective experience we call consciousness. To make this concept more relatable, think of a city at night. Each building has its lights on, representing individual sources of information. If you look at just one building, you might see a few patterns, offices lit up in clusters perhaps. But step back and view the entire cityscape, and you'll notice a much richer tapestry. Streets, neighborhoods, and entire districts pulse with coordinated activity, forming a pattern far more complex and integrated than any single building could produce. In this analogy, the city as a whole is akin to a conscious mind, while the individual buildings are like isolated data processors. The consciousness emerges not from the buildings themselves, but from the network of connections between them. Tononi quantifies this integration using a mathematical measure he calls phi. A system with a high phi value has deeply interconnected parts that share and process information in a way that's highly unified. The human brain, for instance, has an extraordinarily high phi value, which corresponds to our rich inner lives. By contrast, a simple computer, no matter how fast it calculates, has a much lower phi, because its components don't integrate information in the same intricate way. Max Tegmark takes this idea and stretches it across the cosmos. Tegmark, a physicist with a skill for turning bold ideas into rigorous science, proposes that consciousness might not be unique to biological systems like brains. Instead, he argues that consciousness could be a fundamental property of the universe, much like energy or mass. He calls this idea the mathematical universe hypothesis, where everything that exists can be described by mathematical structures. In this framework, consciousness arises when a system's mathematical structure reaches a certain level of complexity and integration. To illustrate Tegmark's perspective, imagine a chessboard. At first, it's just a grid with pieces, each following a set of predefined rules. But as you start playing, the game's complexity grows, strategies emerge, interactions between the pieces evolve, and the board takes on a kind of dynamic life of its own. Now imagine scaling this up to a system as vast as the universe. Every particle, every force, every interaction is part of a colossal game, following mathematical rules that, when sufficiently complex, could give rise to something akin to awareness. In this view, the universe isn't just a cold mechanical machine. It's a system with the potential for consciousness woven into its very fabric. Tegmark coined the term perceptronium to describe the hypothetical substance that constitutes conscious systems. Perceptronium isn't a physical material, but a set of conditions under which information is processed in an integrated and self-referential way. Just as Tononi's phi measures the integration of information, Tegmark's perceptronium provides a framework for identifying the essential characteristics of consciousness in any system, be it a human brain, an advanced AI, or even a network of stars and galaxies. Picture a river. At first glance, a river seems like nothing more than flowing water. But if you place a water wheel in the stream, the river's energy becomes harnessed, channeled into mechanical work. Consciousness, in Tegmark's view, is like the water wheel, a mechanism that arises when certain conditions allow the flow of information to become self-organizing and meaningful. Just as the water wheel transforms the river's energy into motion, perceptronium transforms raw information into awareness. And that leads us to the next chapter. If the universe is alive and conscious, can our minds shape it, just as the observer effect hints at particles obeying the watchful gaze of awareness? Tegmark's idea of a living universe whispers of a cosmos where consciousness is not an anomaly, but a cornerstone. Meanwhile, quantum mechanics reminds us that the simple act of observing changes reality, collapsing a wave of possibilities into a single, concrete moment. So, what if these two ideas are not just related, but inseparable, like two sides of the same cosmic coin? Could our thoughts, our intentions, ripple through the fabric of existence, nudging the universe toward new realities? If the observer effect proves that particles bow to observation, then what does that mean for the vast web of matter and energy that surrounds us? Is it possible that the universe listens, responds, and evolves with our awareness? In the late 1990s, a curious experiment began at Princeton University under the guidance of Dr. Roger Nelson. It was called the Global Consciousness Project, and its premise was as bold as it was unconventional. Nelson and his team placed random number generators, small devices designed to spit out entirely unpredictable sequences of numbers all over the world. These machines were the embodiment of randomness, little digital dice rolling forever in chaos. But Nelson had a hunch that the human mind, when collectively focused, could somehow disrupt that chaos. The project's origins were rooted in earlier studies, suggesting that individuals could influence random number generators under controlled conditions. A person concentrating intently on altering the machine's output could produce results that deviated ever so slightly from chance. It was as if the mind, through some unknown mechanism, could reach out and touch the physical world. Nelson's idea was to scale this phenomenon up, to test whether moments of shared human emotion, joy, grief, fear, could leave a measurable imprint on these random number generators. The results were surprising. During major global events, like the tragic attacks of 9/11 or the worldwide celebrations of New Year's Eve, the data from these generators showed patterns that defied randomness. The numbers weren't behaving as they should. It was as if the collective consciousness of humanity, unified in those moments of intense emotion, was bending the rules of probability. Skeptics argued that the results could be statistical anomalies, artifacts of flawed methodology. But even critics had to admit that the consistency of the findings was difficult to ignore. Imagine the universe as a still pond. A single pebble, tossed into the water, creates ripples that spread outward, gentle but unmistakable. Now imagine billions of pebbles, each one a thought, a moment of focus, falling into the pond at the same time. The ripples begin to intersect, forming complex patterns, waves of influence that spread far beyond their origin. This is how the Global Consciousness Project envisions our collective thoughts as tiny disturbances in the vast field of reality, subtle but undeniable. And yet, the implications of this idea stretch far beyond random number generators. If our minds can influence machines designed to produce chaos, what else might they be capable of? Could consciousness, in some fundamental way, be interacting with the universe's source code, the underlying fabric of reality itself? This question leads us to the realm of simulation theory, a concept popularized by physicist and philosopher Nick Bostrom. Simulation theory suggests that our universe might not be the real universe at all. Instead, it could be an incredibly advanced simulation, a kind of cosmic video game created by an intelligence far beyond our comprehension. To many, this idea sounds like science fiction, but to some scientists, it's a hypothesis worth considering. After all, as our own technology advances, we're becoming capable of creating increasingly sophisticated simulations. If we can do it, why couldn't a far older civilization have done the same? And there is one man that takes this concept to heart. Thomas Campbell's story begins not with grandiose ideas about the universe, but with a quiet curiosity about the nature of reality itself. This pursuit led him into the emerging field of consciousness research, an area that many of his peers dismissed as pseudoscience. But Campbell had a knack for asking questions that others avoided. What is consciousness? Where does it come from? And most intriguingly, could it be the key to understanding the entire fabric of reality? It was during his early career as a physicist working with NASA that Campbell's fascination with consciousness began to solidify into something more profound. He teamed up with Bob Monroe, a pioneer in out-of-body experiences and altered states of consciousness, to study the human mind in ways traditional science had barely touched. Monroe's lab, the Monroe Institute, was unconventional. There were no particle accelerators or telescopes, only soundproof rooms and devices designed to alter brainwave frequencies. Campbell's role was to bring a scientific lens to Monroe's experiments. What he found there would change his life and his understanding of reality forever. Through years of experimentation, Campbell became a direct participant in the phenomena he was studying. He learned to enter altered states of consciousness at will, to explore realms that felt as real as waking life, but operated under entirely different rules. These experiences were more than just vivid dreams or hallucinations. To Campbell, they were encounters with a larger system of reality, a reality that seemed to exist beyond the physical world. As a scientist, he was skeptical at first. Could these experiences be explained by the brain alone, or was there something deeper at play? The more he explored, the more he became convinced that consciousness was not just a byproduct of the physical universe. Instead, it seemed to be the very foundation of reality itself. Over decades of research and reflection, Campbell distilled his insights into what he calls the big theory of everything. Unlike traditional scientific theories, which focus on explaining specific phenomena within the physical universe, Campbell's Big Toe aims to provide a framework for understanding all of existence, both the physical and the non-physical. At its core, the theory posits that reality is fundamentally a digital information system, akin to a vast and complex simulation. In this view, the physical universe is not the ultimate reality, but a subset of a larger, consciousness-based system. To understand Campbell's big toe, it's essential to grasp his concept of reality as digital. Imagine a computer simulation, like a highly advanced video game. In such a game, the characters and environments are made up of pixels, but the underlying reality of the game is code, lines of instructions written in a programming language. Similarly, Campbell argues that the universe we perceive, with its stars, galaxies, and laws of physics, is the result of underlying information processes. These processes, he claims, are governed by a kind of cosmic code that operates in a digital, binary format. At the most fundamental level, reality consists of bits of information, just as a computer does. But where does consciousness fit into this digital framework? According to Campbell, consciousness is not an emergent property of the brain, as materialist science often suggests. Instead, it is the primary reality, the source of everything else. In his model, consciousness operates like the central processor of a vast computer network. It generates the data that forms the basis of the physical universe and interacts with it in real time. In this sense, we are not merely physical beings inhabiting a physical world. We are conscious entities participating in a grand, collaborative simulation. Campbell's ideas can be explained with a simple analogy. Imagine you are playing an immersive virtual reality game. When you put on the VR headset, you are immediately transported into a digital world. The trees, buildings, and people in the game feel real, but you know they are just digital constructs. What makes the experience meaningful is not the pixels on the screen, but your interaction with them. You make choices, solve problems, and navigate the game's challenges. According to Campbell, our physical universe works in much the same way. It's a virtual reality environment created by a larger consciousness system, and we, as individual consciousnesses, are its players. Campbell's big toe also delves into why this simulation exists in the first place. He suggests that the larger consciousness system has one primary goal: to evolve. In this context, evolution doesn't refer to biological evolution, but to the process of reducing entropy within the system. Campbell argues that the LCS evolves by creating virtual realities like our universe, where individual consciousnesses can interact, learn, and grow. By making choices and experiencing the consequences, we reduce our own entropy, contributing to the overall evolution of the system. Imagine for a moment that the entire universe is a labyrinth of ones and zeros, an intricately designed program humming beneath the surface of what we perceive as reality. The stars, the trees, your own beating heart, each one a line of code, each experience a script unfolding in real time. Yet the mystery deepens. What if your mind isn't just a passive observer of this grand simulation? What if it's an active participant, interacting with the very source code of existence itself? Campbell's work takes us down this rabbit hole, where the boundaries between the observer and the observed blur into a seamless, interconnected web of reality. The larger consciousness system, or LCS, in Campbell's vision, is not a deity, nor a machine. It is something far more enigmatic, a vast, conscious entity that continuously seeks to refine itself. But here's the twist: it cannot evolve on its own. For this system to reduce its entropy, it must create conditions where fragments of itself, individual consciousnesses like you and me, can experience and grow. And so, the LCS spawns virtual realities, complex simulations like our universe, as a kind of experimental laboratory. Here, within this simulation, we are tasked with making choices, facing challenges, and learning lessons, all of which serve to lower our entropy, and in doing so, feed the evolution of the greater system. Think of it like a massive multiplayer online game. Each player is a consciousness navigating the digital terrain of the game world. The goal isn't to rack up points or defeat enemies, but to make meaningful choices, to learn, and to evolve. The game's code, however, isn't rigid. It's adaptive, responding to the intentions and actions of its players. In Campbell's framework, this adaptability is where the magic lies. Our minds, through intention and awareness, are constantly interfacing with the source code of the simulation, subtly influencing its unfolding reality. To understand this interaction, consider a phenomenon Campbell calls intentionality. In his view, your thoughts, emotions, and intentions act like inputs into the simulation's code. When you focus your mind, whether through meditation, prayer, or even casual daydreaming, you are sending signals to the system. These signals, subtle yet profound, can alter the probabilities within the simulation, shaping outcomes in ways that might seem miraculous or coincidental. For example, have you ever thought deeply about someone only for them to call you moments later? Or envisioned a goal with such clarity that it seemed to manifest out of nowhere? Campbell would argue that these aren't mere coincidences, but evidence of your consciousness engaging with the simulation's underlying framework. The science behind this idea isn't as far-fetched as it might seem. Quantum mechanics, for instance, has long puzzled over the role of the observer in determining reality. The famous double-slit experiment revealed that particles behave differently depending on whether they are being observed, suggesting that consciousness plays a role in shaping the material world. Campbell extends this notion to the entire universe. If our reality is indeed a simulation, then consciousness is not just a feature of the system, it is the very mechanism through which the system evolves and adapts. Campbell's ideas also draw intriguing parallels with the emerging field of simulation theory. If reality is a simulation, then it must have a source code, a set of fundamental rules and algorithms that govern its behavior. Some scientists and philosophers speculate that these rules could be encoded in the very fabric of space and time, much like how a video game's physics engine dictates the behavior of objects within the game. Campbell goes a step further, suggesting that our minds are not just players within this game, but co-creators of its reality. By aligning our intentions with the greater purpose of the LCS, reducing entropy and fostering growth, we can influence the simulation in profound and meaningful ways. One striking example of this interplay is the Global Consciousness Project. When large groups of people align their intentions, the fabric of reality itself seems to ripple, as though responding to the collective will. Think of a flock of birds. When individual birds fly independently, their movements appear chaotic, but when they align, even momentarily, they create stunning, synchronized patterns in the sky, as if guided by an unseen hand. In the same way, Campbell suggests, our individual minds, when aligned in purpose or intention, can create ripples in the larger system, influencing its trajectory in subtle but significant ways. And yet, this raises profound questions. Campbell's work suggests that the LCS is not a distant, impersonal system, but a living, conscious entity that learns and adapts through us. This means our choices matter, not just to our own lives, but to the very fabric of reality. Every act of kindness, every moment of clarity, every instance of courage contributes to lowering the entropy of the system, helping it evolve toward greater harmony and functionality. And yet, the most tantalizing mystery remains. If we are co-creators of this reality, what lies beyond it? Is the simulation just one layer of a deeper, infinite hierarchy of realities? Campbell hints at this, but refrains from definitive answers, leaving us with a profound sense of wonder. If the LCS evolves through simulations, then perhaps our universe is just one chapter in an ongoing story. A story where consciousness is both the author and the protagonist. From the smallest ripple of a photon to the grand sweep of galaxies, the universe whispers its secrets in patterns, connections, and consciousness. The double-slit experiment, simple, almost childlike in design, revealed a cosmic enigma. Particles obeyed the gaze of an observer as if reality itself hesitated, waiting to be noticed. The Global Consciousness Project offered a strange kind of proof, hinting that human minds might sync with the universe itself. Patterns emerged in random data during global moments of joy, sorrow, or crisis, as though the universe shivered in empathy with us. It suggested that our thoughts, emotions, and intentions might ripple outward, touching the cosmos in ways we cannot yet measure. And so, the big theory of everything beckons, promising a unifying narrative where physics, biology, and consciousness meet. It suggests a universe not as a cold machine, but as a living, dreaming tapestry, where every atom and every star carries within it the spark of awareness. The story of a conscious universe is not a conclusion, but an invitation. To observe, to wonder, to ask whether the universe gazes back when we look at it. Perhaps it always has.